Welcome everyone to this very big, very important event and long-awaited event, which is the release of the first data from our CryoSat mission. As you know, it's always an exciting day for us in the agency and for the scientific community at large when we are about to release the results from our missions. But I think today is a particularly special day, thinking about, looking back at the history of the CryoSat mission. All of our missions are years and decades in the making, but of course CryoSat had a difficult start with a launch failure in 2005. But then last year, more or less a year ago today, 8th of April 2010, we launched CryoSat-2, and now we are now ready to show you the first results from this mission. First, on a very practical point, there will be also translations. All presentations will be done in English, mais pour français, c'est sur canal, traduction sur canal 2. To present the results, we have a very esteemed panel here with Professor Volker Liebig, ESA's Director for Earth Observation Programs, Professor Duncan Wingham from the University College of London, and Professor René Forsberg from the Danish National Space Institute. Welcome. And also in support here in the front, we have Mr. Richard Francis, who is the project manager, and Thomas Parinello, who is the mission manager. Thank you, everyone. Now, as a small appetizer, before we present the results, we would like to show you a 2-minute film from the validation campaign that was done in Greenland in April this year. So we'll start with that.
Ilulissat, icebergs in Greenlandic. A well-chosen name for this town, the third largest of Greenland, located north of the Arctic Circle. Along its coast, a multitude of icebergs are drifting. Ilulissat is next to a huge glacier, the source of these gigantic pieces of ice. This glacier has been in retreat for many years. For the European Space Agency here, all the elements are present to understand climate changes, and in particular, how the ice coverage of our planet is evolving.
You have here many ingredients of what we do and why we do it. You see out here floating sea ice, icebergs carving a bit around the corner. There starts the ice shield of Greenland, a 3,000 meter thick ice cap. And all this plays a very crucial role in our climate system. And the different parameters of the climate systems, it is what we investigate with our Explorer missions.
Climate change is a global issue, and to comprehend it, a global view is needed that can only be given by satellites. Currently, ESA has 5 satellites observing the Earth, giving invaluable data on several aspects, from gravity to ocean circulation, soil moisture to ocean salinity. Among these so-called Earth Explorer missions, CryoSat is measuring the ice thickness with an accuracy down to 1 centimeter. All these satellites are giving facts, data that cannot be questioned like a model can.
We don't speak about models when we speak about our Earth observation data from satellites. We just describe what we see. And as a matter of fact, we see that the sea ice is retreating very much. And in the last year, since we look at the sea ice, we had almost every year a record low of sea ice extent in the summer in the Arctic. So this is a clear indication that the environment is changing here, and very fast.
On the Greenland ice cap, scientists have been able to make detailed measurements of snow and ice properties, required to validate data from CryoSat. The different types of ice and the nature of the snow have been analyzed, and ESA's ice mission is now able to provide key answers to questions such as how fast the Greenland ice cap is melting and how this will contribute to global sea level.
We're here just about on the equilibrium line of the Greenland ice sheet, so just about the point where as much snow arrives in winter as melts out in summer. And the last 20 years here at this location, the melt has increased year on year, so much so in fact that next year they'll probably have to move the camp to take out this climatological change. So this is exactly what we're trying to measure with CryoSat. Of course, here at the camp you can do this very locally, you can do it in the region around and get some very accurate measurements just in the locality. The task of CryoSat then is to extend those measurements over the entire ice sheet.
From its position in space, and in fact orbiting closer to the poles than any other satellite, CryoSat has a unique point of view, and after this ground validation campaign, ESA can now really give the accurate data needed to understand the relationship between ice and climate change.
In the debate in the last few years, I must say, has revolved around some rather small details. If one looks at the broader picture, climate change is here and it's with us. I think the question today is much more seriously focused on regional change and what's happening in parts of the world. And satellites like CryoSat will continue to be vital for that kind of, to answer that kind of question.
And with CryoSat measurements combined with data from the other Earth Explorer missions, ESA can indeed offer the most complete knowledge about the health status of our planet.
So I should not fail to mention that this validation campaign to ensure that the data from CryoSat is indeed correct was also done in collaboration with NASA. But with that, I'm very happy to turn over to our Director for Earth Observation, Volker Liebig, who will present the mission status and give us a little bit on the science.
Yeah, upsala. It's louder than I expected. Good morning, everybody. Yes, as has been said, I will try to set the scenes, and for the two scientists we have invited. What you see here is what happened in the last years in the Arctic concerning the ice extent. This is something we can already observe from satellites since some 30 years. Microwave instruments are usually the source of that. By the way, this is one product coming out of the future GMES My Ocean service. What we could not measure so far is the ice thickness, and this is one of the innovations coming from the CryoSat mission, and I will go into that a bit later with more detail. Here you see also how the situation was in the last years, but especially also in this year. So we have seen, or we expect this year the third lowest ice extent since we have satellite records in '79. We see overall the last years always ice extents which are below the mean value of the last decade. So all these data are clear indication what happens, but what we really want to know is, of course, about volumes, what we have to expect concerning sea ice. But sea ice is not the only interesting area. There is the ice caps, because we have sea level rise, which is at the moment in the order of 3 millimeter per year compared to 1.6 millimeter in the past. So it has almost doubled already. And this comes from a combination of thermal expansion due to the warming and of ice, which is at the moment on land and is melting. And here, without going into details, because here you will also get more information from my colleagues here, you see what's happening in Greenland. And the red, by the way, the red data come from gravity missions like GRACE and GOCE. So you see that there's a strong also increase in melting. And Greenland, as I said already, is the more important ice cap for us compared to Antarctica in terms of the time frame, because what is forecasted at the moment is that there will be a contribution of about 50 centimeter alone from Greenland in this century to the sea level rise, plus the thermal expansion. Why is the Arctic, for climate reasons, so interesting? First, you see here the known surface air temperature development since we measure temperature. So it's this 0.7 degree increase we have seen since 1870, but it's not uniform everywhere. It's a mean value. And you see here, you have here the latitudes. So here's the equator, here is the pole, the North Pole and the South Pole. And you see that when you have here an increase of the order of 1 degree this famous 0.7 degree, then you have at the poles, you have values which are much, much higher, 4 times, 5 times, 6 times this amount. So you have a much stronger temperature change in high latitudes than in lower latitudes. But there's also some geopolitical reasons, economic reasons why the Arctic is interesting. You see here, let's say, a summary of activities which take place already now in the Arctic. And so we have mineral exploitation, increasing tourism, fishery, oil and gas exploration, and what is also coming up, ship routes, the Northern Passage or the Northwestern Passage. They are just much shorter than the classical routes of today via the Suez Canal or Panama. And so it shows also a bit why there is so much economic interest in the Arctic. And this combined with the expectation that in the middle of this century, and this is only 40 years from now, in summer there might not be much ice anymore, so there is a lot of more activities possible, is another reason why this area is a bit in the also political focus right now. What you see here is what in the last IPCC report, the International Panel of Climate Change, was the forecasts, and the red curve is what is observed. So you see that since the last report, I think it was in 2007, if I remember correctly, with data based on publications a bit before, our knowledge has developed very much, and this comes mainly from satellites. So the next IPCC report will show already completely different forecasts for the development of the sea ice in the Arctic. This brings me now to CryoSat. When you walked in, you could see a one-to-one model. So it's a relatively small satellite, and it carries 2 radar systems. It's very innovative. We launched it almost a year ago, and now we can present to you the first ice charts. One has also to know that it takes 370 days, so practically a year, to cover the whole planet. And so it's clear that you also, if you want to make a full map, it takes you a year. And if we want to see the changes, then we add every year, we will add another map, and these change maps are what is most interesting to the scientists. So what are we looking at with the CryoSat? First of all, as I said already, the ice edges. So what is the height of the ice over the sea ice? So here you see the sea ice surface. This is, by the way, an original signal received from CryoSat. And from that, you can calculate how much is the thickness of the sea ice in total, because we know the Archimedes principle, and by that it's relatively easy to calculate that. So this is one thing we will get, so sea ice thickness. This is, I think, the most important one. This is combined with a higher resolution. For the first time, this satellite delivers a resolution of roughly 250 meter in flight direction, which is necessary to distinguish between ice flows and waterlets. That means ice-free areas in between to really calculate also the volumes of ice. So here you see also a measurement with the different colors which represent ice or no ice. This is, as I said, much higher, this resolution, than the one of classical altimeters we have flown on Envisat or EIS missions. So this is one of the first elevation maps, and I don't go into any detail because we have then Duncan and René here to elaborate a bit on that. This is Antarctica, but this is the second subject. It's sea ice is the one. The other one is the ice caps. We have 3,000 meter high ice caps, and they represent an enormous volume of water. If we take only Greenland, which is a smaller one, but for us more important, this represents about 7 to 8, 9 meters of water level, if everything would be molten. In Antarctica, it's much more. But this will also take a lot of more time. Nowadays, scientists are not using only the information from one satellite, but combinations of satellite data. And what I want to show you here is leading us to the third subject, which we can measure with the CryoSat satellite. So if you take classical altimetry data, you get the sea surface and its changes. And when you subtract from that the geoid, so the gravity information, then the difference between the two represents the ocean current system, or as we call it, the ocean dynamic topography. And this, in combination with CryoSat information on where is water, where is ice, gives us the possibility to, for also Arctic waters, for example, to calculate ocean current systems. And this is one of the maps where you see the highs and lows which were calculated with this method. And you remember that the geoid from Goji is accurate enough and was exactly designed to develop and to find the current systems in altimetry data. And so here you see a map which represents this ocean topography when you reduce it by the gravity field. And this represents these current systems in the Arctic, which you see here. So these are the three topics we will address: sea level, ice thickness, ice cap thickness, and ocean currents. And for all three areas, the CryoSat mission delivers the data. This brings me to my last slide. The CryoSat mission is working perfectly. It was also placed in the orbit very accurately when we launched it. So we have saved a lot of fuel. And due to its health, we will be able to operate CryoSat much longer than expected. It was planned to be until 2013, but we have, from the actual point of view, the possibility to go at least 4 or 5 years longer. And for that, we have an important event next year, which is our ministerial conference of ESA, where we will ask the ministers to subscribe again for the Earth Observation Envelope program, which is the mother of all these activities of the Earth Explorer. And I will also include the proposal for extending those missions. But for that, we need a good contribution from the member states. So this is the link to what will happen next, probably winter, November, very likely 2012. Having said this, I would like to hand over to the next speaker.
Thank you, Professor Liebig. The next speaker is Professor Wingham. Professor Wingham is what we call the principal investigator, which means that it's through him all the scientific community works with the scientific data. So now we'll have a presentation about the science.
So thank you. Good morning. Thank you, Volker, for a nice introduction. So what I'm going to talk about are the results that we've managed to get more or less from a year since the satellite was launched. I thought I would start with two brave sentences that I wrote in 1999 associated with the mission, just explaining what we were targeting. I say brave because at that time it was a concept, but essentially what we had to do was first, as far as the ice sheets were concerned, ensure entire coverage of the sheets, because the previous generation of instrumentation had not given us the last 50 kilometers going into the coast where a lot of the ice turnover is. And we also had to add a resolution capability that, just as Volker explained, we could pick our way between the floating ice and the leads in between if we were really going to get down to total Arctic volume. So that's what we were shooting for. Already been mentioned, of course, that we had a few problems along the way, but we did go off smoothly. It's in April 2010. So nice photograph, just the moment of main engine start as the satellite, as the rocket comes out of the silo. And if you look closely, you can just see there the pilot ejecting as it goes up. So here's the first main result then. This is a DM created from CryoSat data recorded February-March 2011. You'll see all of these results are from 2 months of data, and that's because we've quite simply spent the last year or more, I say we, I mean us at UCL, but I also mean at ESA, working very hard to squeeze out all of the bugs in the ground segment. So we have really more or less 2 months of data, and to do this job properly for the Arctic, we need to use, for the Antarctic, we need the full repeat, which is a year or so of data. Nonetheless, what you can see immediately is that we are gaining coverage all the way down to the coast. So we have, for example, complete coverage of the Pine Island Thwaites sector, currently losing of the order of 200 gigatons of year of mass into the ocean. We've got complete coverage of the East Antarctic ice streams coming down into the Ronnie Filchner. But the real test is there. That's Lower Dome. And previously that was completely invisible before. Just behind the back of the Lower Dome there is the largest glacier on Earth. That's the Totten Glacier. That's pulling mass out of this huge basin, East Antarctica. And this basin is also losing mass. And you can see just with 2 months of data, we beautifully pick it up. So a preliminary result, no doubt there are flaws in this. You can see the odd poor piece of data in there, which in 2 months you can't do much about. But immediately we can see that we achieve this main mission goal of providing complete coverage of the entire ice sheet. One of the features we've added to use that data that gives us complete coverage is the interferometer. The interferometer is a complex system. We have the 2 antennae cross-track, then we have a bench, and then on top of it we have the star trackers. So all of those elements have got to work perfectly together in order to get that interferometer to work. In the last year we have been calibrating this interferometer, and for that you need a known surface. So rather than using the slope of the ice sheet, we've been rolling the satellite over the known surface of the ocean in order to calibrate the angle measurement of the interferometer. Well, that's all gone very smoothly, and we get a nice straight calibration curve, and it's all in spec. So just to see what we could, having calibrated it, it could really do, we took a strip of data, sarin data across the Pacific, and we chose it so it runs up this Seamount chain, which comes from Hawaii up to the subduction zone there. This is a mantle plume coming from deep in the mantle, and as the continental drift goes over it, it pushes up this line of underwater volcanoes. And those are sufficient to cause tiny deflections in the shape of the ocean surface. And what we tried to do is see if we could measure those deflections. Well, here's the result. So the darker line is airborne gravity over those seamount chains. These are accurately measured because of the geophysical interest in the seamounts. And the lighter curve on top, albeit more noisy, is the CryoSat interferometric measurement of the cross-track slope. What you can see is it's perfectly following the larger deflections. You can see we've got a noise level of around about 20 microradians in the interferometer measurement. 20 microradians is an extremely small angle. And it's worth perhaps also remarking that people have been talking for 20 years or more about measuring cross-track slopes in the ocean using interferometers. This is the first demonstration that you can actually do it, and a very nice demonstration it is too. And just to illustrate how nice a piece of kit we have on this satellite, I've just put on there the specification of the error bar. So if this instrument had met its spec, what this figure would have shown you was just a whole load of black noise. So you can see we're down at something like 6 or 7 times the original specified performance. And I can see some instrument representatives at the back there, so there's a nice demonstration of the beautiful piece of hardware that you've put up for us, I must say. So turning to the sea ice, this is an image I know some of you will have seen before. We generated it quite soon after launch, and it shows that more or less we're getting the echoes that we need to get from the sea ice. But it's worth remarking that that's the easy bit. So the hard bit of this measurement is first you have to distinguish these leads. So there's a lead, there's a lead, there's a lead. So that's the exposed ocean surface. And then you've got to distinguish that from the top of the ice, which is this tiny green line running across the top there. And as you can see, if you look at the scale, that offsets of the order of 10 centimeters or less. So the hard part of this is that measurement. We've designed this radar to, first of all, resolve the differences, which is why you can pick the leads up by eye. But we've also designed it to give us extremely clean echoes. In the past, this would have all been blurred out. So we need to do 2 things. We need to get the ocean surface first. So here is more or less the same figure that Volker showed. It's the difference between the ocean topography that we've measured and a gravity field. And can we verify it? Well, that is an ocean model. That's the 12th degree NEMO model being run by the National Oceanography Centre in Southampton. And what you can immediately see is that we're picking up all of the detail that you see in the model. We nicely capture this boundary layer flow through the center of the Arctic. We capture all the detail of the Beaufort Gyre, which is the big red spot. We capture the high sea levels down the edge of Greenland here. Of course, that's a model, and I'd be the last person who wants to verify a measurement with a model, but it is worth observing that we must be good to of the order of 3 centimeters already. So we are down to 3 centimeters accuracy within 2 months of data. So can we do the sea level part of the problem? Yes, we can do the sea level part of the problem very nicely, and we're not even trying really hard. You can just see, if you look very closely, a kind of odd flicking here. That's the telltale that we've only got 2 months of data, and we need to build up over time to get that sea level really tight. But that's not a bad answer with 2 months of data. So let's turn to the ice itself. This was really the primary objective of the CryoSat mission. There's a picture of the thickness of Arctic ice, January, February 2011. So some obvious points about it. We more or less get complete coverage of the Arctic for the first time. So we can see all of the concentration of ice in the North Pole as it's caught between the 2 great circulatory systems. We've got it at enormous resolution. You can see linear features in these data caused by compression ridging in response to the wind stress. I don't know whether you can quite see it, but you can see some squares on here. I can anyway. Those squares give you the size of the resolution cell that the mission was specified at. So we're pulling out detail from the sea ice, which is about 5 or 6 times higher resolution than the mission was specified at. You can see quite subtle variations of thickness in the Beaufort. Then you come into the Lincoln Sea. So really a marvelous thing. And of course the question is it right? Well, RV, Alfred Wegener Institute, flew 2 lines for us to do a quick validation. One up here in the Beaufort, one down here in the Lincoln Sea. So in the Beaufort, they found a mean thickness of 2.7 meters thick, and that's more or less exactly what we're finding. And in the Lincoln Sea, mean thickness 3.8 meters, which is bang on the nail too. I should say, we only did this recovery of the thickness in the last 2 weeks, and we only got the validation data last Friday. So it's plainly a fact that we have not had time to tune these differences. This is just stuff straight out of the can. So we're getting these thicknesses correct as far as we are able to determine. And the other question is, are we capturing the detail correctly? I mean, is that real? Is that structure real? Well, here's another satellite image, but what this is showing is the distribution of ridging in the Arctic. It's a scatterometer off from one side, so if the ice gets ridged, you get a high signal. If it's first-year ice, you get a low signal, so you can see where all the ridged ice is. And what you see is a very nice agreement with the thick ridged ice over here. You can pick up that feature there, there. You can pick up that feature there, there. So it would seem that, at least down to scales of the order of 50 kilometers, we are perfectly mapping the thickness of the ice. And no doubt in time, this will also be of enormous importance in improving models, because we can now, in detail, understand how the ice is fracturing and compressing in response to the wind stress. But I think the real headline is that Volker was showing curves of ice extent. I'm sure you've seen these things for years now, and they've been visualized. Ice extent is not ice volume. And you cannot disentangle from those plots whether the ice is actually shrinking or simply being blown up against Canada. And as soon as you see thickness, you realize how much ice is being blown up against Canada. It's being generated over in Russia, pushed over here to Canada. Some years you just get thicker ice because it's blown there. So this is really the first data point on a new time series of sea ice thickness, which isn't aerial extent at all. It's actually the thing you need to know, which is volume and hence mass. And so here it is. There's the first nice data point. And I have to say, when I saw that, I was a relieved man, because I did pitch this quite a long time ago, so it's very nice to see it come out. So, okay, by way of conclusion, the CryoSat payload continues to meet and usually considerably exceed its specifications. So it really is a very fine piece of equipment. The preliminary verifications, because this is quite quick, show that we will meet or exceed the geophysical specification. In other words, what it was designed to do from a geophysical point of view, rather than a technical point of view. We will provide synoptic, accurate Arctic-wide ice thickness and volume, and in unprecedented detail. I've never seen it before like this. And it will provide us with coverage of the continental ice sheets right from the center to their coasts, right from their centers to the coasts. And I think this other point, which Volker was also bringing out, is that although it wasn't sold this way, you can already see that we can do the entire dynamic topography of the Arctic Ocean, which means we can derive the ocean currents of the Arctic Ocean, which has also never been done before. And I've no doubt that once we use GOCHE, which we haven't thus far, we'll be able to nail down those 4-5 centimeters that I was talking about a bit earlier on. So I must say, from my, and I'm sure other people's point of view, it's a very nice preliminary outcome from the mission. Thank you.
Thank you, Professor Wingham. Now, the CryoSat data has a lot of concrete applications for government and commercial activities. And to speak a bit about those applications from the user's perspective, we have Professor Forsberg. So I'll let you introduce it.
Okay. Yeah, it's a fantastic data set coming up, but as you realize from Duncan Wingham's talk, we're still very much at the start of the data flow. So I'll mainly show some general uses and a little bit of what we've got earlier from other satellite missions. So my name is René Forsberg. I'm from the Danish Space Center, but do work a lot in Greenland, so there will be some Greenland focus on this thing, this talk here. Well, you can see why the Greenlanders are so interesting in ice, both sea ice and inland ice. This is one of the cities of the west coast of Greenland. People literally live on the ice. Their living is driving out on the ice and fish and hunt and so on. So what are the main applications from a science point of view for CryoSat? Obviously, that's to find out what is happening to the big ice sheets. That's one of the most political things right now. What will happen to global sea level rise? You really need the quantitative data of what is going on. And I like what Volker Liebig said here, that ESA give hard facts and not just models or politically tinted statements. And that's really nice here. We do already have some missions up in space, an American-German mission called GRACE, measure the gravity field changes over the ice sheets. It gives you not the high resolution, but it gives you total mass. And if you take this kind of plots of what the measurement of these satellite gravity missions give, it will tell you how many gigatons of ice disappear every year in the ocean. And a gigaton, that's a square cube of ice, 1 kilometer on each side. So there's a lot of water going out, giving you the sea level rise. What you can see when you see these time series is that in the last years, 2007 and 2010 have been abnormal years where you have extra much loss of ice. And this means that the CryoSat satellite being thought out by Duncan Wingham in a proposal in 1999 is really way ahead of its time, and only now do we really see the big benefits of being able to monitor these things in real time, and CryoSat will help tremendously in this aspect. So we'll give input to the debate of climate by providing hard facts, and we'll build on earlier missions which tried to do this, but only with a limited resolution and a limited time sampling. ICESat, an American satellite which had a laser in space, but which only worked 2 months a year, and GRACE, which was this gravity field mission. So we'll increase accuracy and everything. Here's just some examples. We do already have an indication of what's going on. Duncan Wingham mentioned in Antarctica the Pine Island glacier system. It's a major loss of Antarctic mass. It decreases in height by about 0.5 meter per year. This you can see from the laser measurements. In Greenland again, you see the areas on southeast Greenland, on the northwest coast of Greenland, and we're really waiting now to get the much higher resolution and the all-weather capability of the CryoSat radar. To understand the data, you need to find out this new technology, what is it doing? We have fancy radar technology, interferometric radars, narrow footprints. They are not bouncing off the top of the ice or the snow. They are bouncing off somewhere a little bit inside the ice and snow. So we have these big campaigns. You saw some video in the beginning. It's sending out aircraft on the ice, having scientists on the ground drilling into the ice, finding out where is the radar reflections coming from. And also on this Greenland aircraft, our people flew it with the airborne model of the CryoSat radar called the Asira. So they were flying a lot of profiles over land ice and sea ice in Canada, Greenland, and Svalbard, and collecting these data, showing how the echoes from the ice sheets are coming in from the different layers of every year's small melt. This will be a variable data to get down to the centimeter, which is required for all these understanding here. There's also a large interest, not just from the scientists, there's also interest from the government. And the governments, of course, are very concerned about sea level rise. And we already heard that the global ocean is rising about 3 millimeter per year, and there's different satellite missions since 1991 measuring the ocean surface height with altimeters going up through the years, which shows that we still have this rough linear rise. We haven't seen any real acceleration yet, but everybody expects an acceleration. And there's predictions of 0.5 meter, maybe even 1 meter by 2100 in the UN IPCC reports. What we have to realize is that these predictions assume that suddenly the ice sheet will start to flow faster. That means to detect if these things really happen, you need to have satellites in space who can say, well, now it's happening or now it's not happening. So that's the real value of these things. One thing we have to make sure, be aware of, is that when the ice sheet, for instance, of Greenland melt, everybody maybe think, well, then the whole ocean will go up at the same level everywhere. This is not the case at all. Because when the Greenland melts, the land of Greenland come up, and the gravity of the ice moving away will actually change the ocean surface. Ocean surface depends on gravity field. So actually, if you take the current rate we believe we see in Greenland from another mission, the ISAT mission, which terminated in 2009, and say how much is the ocean surface rising at the current rate of the Greenland melt, we get this plot. It actually shows that even though you put in a lot of water in the ocean around Greenland, the Greenland ocean by itself goes down. Whereas where you really hit badly is the Pacific Islands. It's very strange, but this is a nature physics of the Earth's consequence that the ocean rises the most, the farthest away from Greenland. And actually in Europe, we are right on the 0 level, so we are more concerned, should be more concerned in Europe with Antarctica than with Greenland, even though the Antarctic total melt is only half of Greenland. But of course this will change in the future if the climate gets the way people predict. So sea level rise by general is very much a government application of CryoSat. Then there are a little bit more direct applications also. People want to know, for instance in Greenland, what's happening to the ice sheet. When the ice sheet is going back, they can start mining and stuff like that in the ice sheet margins. They also are building in Greenland a lot of hydropower plants right now. The Greenland government wants to be green. They want to switch from fossil fuel to hydropower. They got a lot of hydropower when the ice melts, but they want to make sure that the ice don't melt away. If you first build a big hydropower plant, and then the ice melts away and the water runs down the opposite valley, then they have a big loss. And that's why we do, for instance, right now a lot of airborne work from our group to monitor some of these ice margins, but in the future we can use CryoSat. That's quite a big advantage. Also things like the mining things. Here's a big molybdenum deposit in East Greenland. It's right at the edge of the ice, and as the ice disappears, especially here on the margin, there can be access for the people to go in there and get the mining done. Going to the other area, the sea ice, that's also an area, of course, of big government research interest. What we want to do with the sea ice in the science, of course, is to find out if these curves, which Professor Liebig already said, what is the yearly cover of sea ice? Will this sea ice continue to decrease? Here in the red, right on the low here, this is the 2011 sea ice coverage, not the thickness, but the area. And we can see this year the Arctic sea ice coverage is at least right now at an all-time low. We are following maybe the lowest curve or maybe not. That remains to be seen. It's still very difficult to predict ahead from now what will happen in 3 months on the sea ice. The way the CryoSat measure the sea ice, there's a lot of science problem to this. Professor Liebig again mentioned use Archimedes' law. This is an idealized scheme of an ice flow on the ocean. It's really like what you learn in the school. That if you have an iceberg, a certain percentage of the iceberg stick up. So what CryoSat really measures is not the thickness, but it's how much does the ice flow stick out of the ocean. But because the ocean surface is a function of tides, winds, currents, and the gravity field, if you know these things, you can improve the determination of this, we call it the freeboard. But once you measure the freeboard, there's complications. You need to measure know the density of the ice. You need to know how much snow is on board. These are real science challenges to get these things correct. And that's again why we have the campaigns, comparisons to submarine data, comparisons to in-situ data, airborne data, and so on. This plot, which Duncan just showed, we have earlier versions from this with ISAT, but what CryoSat is going to deliver is much more accurate versions of the same thing. So we look very much forward to that. So the research challenge is to measure the flow density structures, air inside. It's to utilize the synergy we have with GOTCHA satellite, especially measuring the gravity field, finding out where is the radar signal coming from. In the summer, sea ice will have small lakes on it, and it's sort of used to screw up very much the satellite measurement. But now with CryoSat, we have some hope we could do it throughout the summer. Here's just an example of data to give you some feel of how it looked. This is from January 29. It's a traverse going across the Arctic Ocean. The plot on the left is 3-day worth of CryoSat data in a year we completely filled. And when you see here is what the CryoSat height is shown in black. And you have the GEOID, that's the measurement from the other ESA mission, the GOES mission, which tells you where the ocean surface should be. And you can then mix these measurements of where is the ocean plus ice surface with where should it be, get some calibration at the thin ice leads occasionally, and you can get nice nice maps also here of the freeboard. Here's an example of this profile. It's another map showing a little bit what Duncan said. It's actually a Russian ice map showing what we call multi-year ice. That's several years old ice, which tend to be thick in red, and first-year ice frozen since last summer in green. And as you go across this profile from Russia towards Greenland, you can see the freeboard building up. It's a very noisy signal because the ice is, by definition, very, very erratic and noisy. You can see all the leads on SAR radar images. But what we do see is that when we pass the thin green area, which is the thinner expected ice, we also see the lower freeboards. But getting all these data in shape, getting an average distribution of ice, this is the main challenge now for the coming months for the scientists. But I just noted Duncan's measurement or north of Canada was 2.7 meter, I guess. And if you look at our mean here, it's 40 centimeter, but this is the freeboard. You probably should multiply by 6.5, and we get very consistent results here. So what are the applications for this sea ice data for government use and commercial application? Well, especially right now, there's a lot of focus on shipping, and the Northeast Passage is actually pretty much open in the summer. You need a Russian icebreaker being standby, but several companies have sent ships through now. There's a German company who started, and now there's a Danish large company called Torm. They are sending ships through routinely now. So they're very keen on understanding what is going on up in the Arctic Ocean. But there's also a lot of heavy icebreakers, nuclear Russian icebreaker. This is a Swedish icebreaker in the back. A lot of icebreakers go up there on cruises for research or for government work, geophysics and so on, and they're really concerned how thick is really the ice, because even a nuclear icebreaker, once it hits 3.5 meters thick ice, they get into problems. Finally, also, when the ice goes away, it hurts a lot people who live from the ice. That's the traditional Inuit way to hunt and fish. So there are pros for Greenland, but there's also negative things for Greenland coming out of these ice changes. So that's why we have CryoSat. We were going to see it quite actually being used by the Greenland governments. There's some interest, of course, in Greenland to open areas where the ice would be thin enough or absent for oil and gas exploration, but there's also a lot of concern about what to do with traditional hunting and what to do with the fishermen who live by fishing from the ice. That's why they have asked us to fly. We've done that a number of times. We fly campaigns with airborne lasers to measure the ice thickness off the west coast of Greenland or the east coast of Greenland, and now again we can switch to CryoSat. So that will be a major help also from a government perspective. Special applications, I mentioned that a little bit, but we have this synergy between measuring the gravity field and what CryoSat can measure. And when you measure with CryoSat, you measure the snow on top of the ice floes and the ice-snow interface, but you also measure indirectly the ocean height. And since the ocean, by definition, always follows what is below the surface, the gravity field change. If you have heavy minerals, a big sea mountain below the sea, the ocean will make a bulge on top of this structure. And these bulges, you can then use the sea level you measure and invert them back to gravity. And this is the same quantity which is measured by the GOES satellite. And you combine these things, and then you could get very nice features from the Arctic, showing all the details of the bathymetry and the geology under the Arctic Ocean. This is an earlier map from another satellite, the IceSat again, but with the CryoSat data you can expand it nearly up to the pole and you will get a much higher resolution here. And you can use this for government interest, things like the ongoing work to make new claims for continental shelf made possible by the UN laws of the seas. So there are a lot of nations right now active collecting a lot of geophysical data up there. And there will be a lot of other applications for that, like what we just saw, mapping the ocean currents and the mean dynamic topography. Okay, so in conclusion, I would say that second year Duncan Wingham and Professor Liebig here, that CryoSat is already a large success. And the data are readily available. We can download them without big fuss from the ESA center in Italy, ESRIN. And we expect this to be continued to improve. And we also see that CryoSat produces essential data for cryosphere research, year-round data, accurate data, and high-resolution data, which we never had access to before. And it's really of the utmost important to the climate debate, because this is facts. This is not models or speculation. And there is also some spin-off, which was probably never really thought into the mission, which is a science mission, that you can get these very politically important things like the sea level rise on a global scale, and help shipping, tourism going up into remote areas, hydropower, and so on. Okay, that's all I would say, but if the guy's out there, he should push the button. There's one guy's just rather close. I'll just show you, this is how the Arctic Ocean actually looks. That's what we are talking about. This is a combination of ridges, multi-year ice, and up here there's the first-year ice. And since we are at an air show, I thought we would show how the scientists left out there to collect the CryoSat ground truth data. They are landing right now, and here's a small ice camp. This is the sea ice north of Greenland. That's the whole game. That's to understand what is happening to this in terms of thickness. So thank you.
Thank you, Professor Forsberg. Very interesting presentation. So now we leave the word to you to ask your questions. I have my colleague here with a walking microphone. So when you announce yourself, please say the media you're from and your name. Here in front, please.
Peter deciding with Space News. Ultimately, should CryoSat be an operational mission that has no end? Or is there a law of diminishing returns here after 5-6 years that you could repeat every decade or so? Or ultimately, should it be part of GMES and with no end?
Well, maybe I try. There's not a definite answer to that yet. CryoSat-2 is a science mission. It's part of the Earth Observation Envelope program. I think it has many ingredients of a future operational mission, and the need for this type of data will not stop after we retire the mission. I think the first step is to run this mission as long as possible, as long as it is working. The investment is already done, and I already mentioned that for that we need support from the ministers next year. But then we can think about making also an operational mission out of that. Potential operator could be, I say, EUMETSAT, without having spoken with EUMETSAT about that in a concrete term, because there's still some time. But I think we have a couple of missions which have the potential to become operational missions, and we have to see how we manage that the scientists on this planet get this data continuously.
I appreciate the scientific interest, but I was thinking from an operational basis, more along GMES, there are lots of communities that both you two mentioned here that are going to have an interest in this data on an ongoing basis, not necessarily daily, but monthly, I suppose. And depending on what you foresee as the economic activity up in that region, maybe on a daily basis, I don't know. But for now, CryoSat is not part of GMES? No. Okay.
No, it's, as I said, it's part of our Earth Observation Envelope program, which is usually the father of all what we develop. And only after that, the step comes to operational missions.
Jonathan Amos, BBC News. Just to continue this discussion, I mean, Sentinel-1 would have the same capability, I think I'm right, but it's not flying far enough north. So, yes, I mean, that's the issue, isn't it, is you've got conflicting orbits. Yeah, you can't do the stuff around the center of the Earth as CryoSat can do around the top.
Okay. I mean, I think that probably the better way of thinking about this is that, I mean, first we need to go on establishing just how accurate and good the data are. So, and I think one needs to appreciate that it may take some time for the use of these data to spread out into communities that will then start to use it operationally. And if that happens over the next 2, 3, 4 years successfully, then I think it's the case will make itself that this is a mission that or a continuing mission that will then in due course have to be operationalized. it's probably just a little bit premature to do that, and also in addition, the communities that could make use of these data operationally need a bit of time to learn how to do it.
Maybe allow me to add, so Sentinel-1 is not a CryoSat. Sentinel-1, because you mentioned it, has the capabilities of Envisat. That means radar images you get from SAT. So you see the I610, but you cannot measure the eye thickness because you cannot measure the freeboard. For this you need this specific interferometric altimetry technology, which is on CryoSat.
Others with questions?
Well, is there anything like CryoSat planned by any of the other space agencies in the next? Are there any other missions like CryoSat being planned right now? NASA has one that's a little similar, but I'm thinking of China or India. Anybody else looking at this as we speak with more than just ideas, with something that's actually in development?
Not to my knowledge. As you say, in the decadal plan of NASA, we have ISAT-2 with the same limitations compared, or with the same differences, I should say, because it's optimized for other things compared to CryoSat. So with CryoSat, we come to 2 degrees to the pole, which is unique, and we have this high resolution. These are the 2 features which are typical for CryoSat.
But maybe a more upbeat point. I mean, my experience has been that if you fly a mission for the first time and it's demonstrably successful, other people will fly more missions. So all we have to do in the next 2 years is show that it's demonstrably successful, which of course we will.
Volker, since you mentioned the ministerial, I mean, this is peanuts, but how many peanuts do you need to keep operating from 13 to 17?
Well, we don't speak about peanuts because it's it's not only this mission. We have shown you some months ago Goche. We have ESMOS, which is another data set, soil moisture, ocean salinity, very important for this thermohaline conveyors belt in the ocean, which drives these current systems. So all these missions, fortunately, have a longer lifetime expected, and the biggest part is Envisat, which we might extend another year, because we want to bridge the gap until we can launch the first GMES satellite. So if I take all this together, we have a lot of money we ask for. On top, we want to build the next explorers. So all this is in the envelope program, and we speak about an envelope for 5 years in the order of 1.8 billion, out of which about, let's say, 100 million is for extending all these missions until they really reach the end of the lifetime. But other parts are the development of Earth Explorer 7 and 8, and start with 9 and 10, make all the technology developments and all the exploitation programs, because we also develop a lot of products coming from that. So we support the scientists to develop the algorithm, the processing and all this. So as I said, Earth Observation Envelope Program is the mother of all the activities which go later into GMES, into the EUMETSAT programs, so into operation.
Any more questions? No, but then I think we will end here. Thank you very much for coming for this presentation of the first results from CryoSat. This is, of course, an evolving story, and I look forward to another press conference in maybe a year's time on where we can show the trends. Thank you.